All right, so we're talking about Monte Carlo method today. If you remember, what we've talked about with radiation so far is black body radiation exchange, and then when you have exchange between two surfaces, the fraction of light or fraction of radiation going from surface 1 to surface 2 is described by the view factor between those two surfaces, from 1 to 2. There are several methods we've talked about for evaluating the view factors, including inspection, library values, rules for evaluating them. There's often situations though where you can't actually use any of those things to evaluate your view factor. Or maybe you want to get a little bit more information than just a view factor in a radiation problem. Monte Carlo methods allow you to do that. So we're going to talk about how to write a Monte Carlo program, and then you'll get a chance, like I said, to practice this in your homework problem. Okay, so what is Monte Carlo method? It's kind of a funny name. The name comes from the casino, right? The casino or the city in Europe. So the idea is that you're basically playing a game of chance with your model. You are putting out a sample, or you're taking a sample of your problem, of a possible outcome in your problem, many, many times, and accumulating the results of that sampling process, and then making some judgment about the average value that you get from that. So it's called Monte Carlo or roll the dice method. So some of the characteristics of this, right out. Some of the characteristics of Monte Carlo methods are that it uses random sampling. Random sampling to estimate a value of interest. Some value of interest, and this value, in our case, could be the view factor, right? Monte Carlo methods are really common, not just in ray tracing or optical methods, but they're really common in a lot of different situations where it's easy to come up with one realization or one outcome for your problem, but it's hard to estimate on average what's going to happen. Okay, so it uses random sampling to estimate some value of interest. It's what we call stochastic. Right, stochastic, sort of a synonym for probabilistic. So it's based on probability. It is not a deterministic method. So stochastic versus deterministic. A deterministic method is something like, I go to a view factor library, I plug in my parameters, and I get back a single value. Right? It's deterministic. I do one thing, I get back one answer every single time I do it. In Monte Carlo methods, you can do this simulation as many times as you want. You're not going to get exactly the same results every single time. You'll get something that's sort of bouncing around the true value. Okay? So it's what we call stochastic. The third thing is that, and the thing we really care about, is it accommodates a lot of things. So it accommodates it accommodates real surfaces. Right? Real surfaces, including things like gray surfaces, semi-gray surfaces, something called specular, which we'll talk about later. So specular is something like a mirror, right? A mirror has good specularity. It preserves the orientation of light coming into it. So you can model specular surfaces. You can also model odd geometries. All right, so those are some of the characteristics of Monte Carlo methods. Let's talk a little bit about the actual method. Okay, so the actual method, what we're going to do is I'll kind of walk through an example on this. So let's draw, let's say a coordinate system. So we have some coordinate here, z, some coordinate x, and then, this will be y. And then this will, coming out of the page basically is x. So let's draw a surface in this coordinate system, something like this. Okay, so we have a surface in this coordinate system. It's in the xy plane. And our goal here is to figure out the view factor from this surface, right? This is going to be our surface 1. Surface 1, and we want to figure out the view factor from surface 1 to some other surface, which we'll draw up here in space. This is going to be surface 2. Right, so our job is to calculate F1 to 2. So what we want to do is, the general method is we're going to take our first surface, the emitting surface, and we're going to just pick a random spot on the surface. So how do I do that? Well, I would say, let's get a random number generator and let's pick a number from 0 to 1. And then let's multiply that by the coordinate, right? So let's multiply that by the maximum extent in x. So let's say first I sample in my y direction, and I come up with a y direction point here, and then I sample in my x direction, and I come up with an x point here. Right, so now I've just pinned down from random sampling my coordinate to be right here on the surface. The next time I do that random sampling, of course, it's not going to be in the same place. Right, so I'm going to get some representative population of possible emitting locations on the surface. Okay, so let's see, I've got to write these down. So step 1, I'm going to randomly select a location on the emitting surface. Okay, randomly select that location. Step 2 is I'm going to choose a direction to emit the ray. Okay, so I now here have this ray that I've picked out at this location. So this ray, if it's a diffuse surface, that means it's equal probability to go in any direction. So it's equal probability to shoot off away from the surface entirely as it is to go to the surface. So I need to pick a random direction. In order to do that, I need to have some coordinates that I'm sampling. Right? I need a coordinate system where I can say, here's my coordinate, here's a random version of that coordinate, and then just assign it. So let's draw a little coordinate system here at this location. So I've got, let's see if it's a little hard to draw small, but I'll try to do this. So here's my coordinate system here. And what I'm going to do is I'm going to pick, let's say we pick a ray that's going in this direction here that's actually going to hit the surface. All right, so I've got a ray here that's actually going to hit the surface here. And what I want to do is show how I got to that from random sampling. So let's draw 2 angles that describe the position of this ray. So 2 angles would be, one is going to be this angle between the normal and the ray, right? So it's like if I had a ray that was straight up and then sort of off to the side, there would be this angle between the ray and the vertical, right? And we'll call that angle theta. We'll call that angle theta. And so these are polar coordinates. Right? In polar coordinates, I have this angle theta. That's the angle from the vertical, and then I have an angle that's sort of like a azimuthal angle, right? And that will be this angle down here, which we'll call phi. Okay, so I'm going to randomly sample from theta and phi and pick a direction for this vector and send it off into space. Okay, so that's step 2. Select a direction to emit. Okay, step 3 is going to be something we actually, so if we had gone in order and not talked about this before, real surfaces, you'd know a little more what I was talking about here. But one of the nice things about Monte Carlo is that it can handle real surfaces. And real surfaces means that it may not emit like a black body, right? So you might want to, in the process of simulating your surface, actually accommodate specular dependence, like spectral dependence. So spectral dependence is things change as a function of wavelength. So step 3 is going to be, I'm going to pick a wavelength. Pick a wavelength for this ray. And then depending on what the wavelength of this ray is, I might either that surface might accept that wave or it might not, or it might pass through it or whatever. I mean, you can do different things based on whatever the wavelength of that ray is. Right, so this is going to now be at wavelength lambda that we've randomly selected. Okay, step 4. Let's see, step 4. Step 4, really the only tricky part is figuring out whether or not this ray actually hit the surface. So determine if ray hits surface 2 or target surface. Okay, so what you're going to need to do here is you have to come up with some test for whether or not this ray is going through this polygon or some shape. So you might, hard code in your program. Here's the rules that I know result in hitting this surface. If that surface happens to be in, say, the XZ plane, it's a lot easier to do than if it's sort of randomly oriented in space. But with if you remember back to your Euler angles, right, the transforms for coordinate systems, by going back to dynamics, it's not that hard to do. You just have to look it up. But you can go through and you just have to determine if it hits the surface. Okay, so if it hits the surface, great. We put it in the category hit the surface. If it doesn't, put it in the other category, and then we just repeat this. So, repeat n times. Okay, so I repeat this however many times I want, enough times where the problem converges. And eventually I decide that things are not changing anymore and I have a good estimate for whatever it is I'm thinking about. So if I'm counting the rays, it's number of hits divided by the number that I sent off, right? And that's going to be the total view factor, right? So my calculation for view factor for 1, 2 would be the number of hits divided by the number of rays, right? The number that I sent off from the emitting surface. Okay, so the underlying idea is really pretty simple, right? It's just that the implementation of it sometimes gets a little bit hairy, right? It's a little tricky. But yeah, I mean, that's basically the premise.